Swayam Prabha. Digital India. Educated India.
Welcome. So we are in fourth lecture of this module. So here we will discuss another type of locking that we experience in finite element method, especially for plane strain and 3D bodies. So here it is called volumetric locking. So now as we have seen, so what I wanted to discuss is that first I will discuss about what is volumetric locking, and then what is the problem associated with a brief I will try to explain it in a from a matrix point of view instead of giving its mathematical background. So now then we'll consider that selective reduced integration, that technique which we have already learned in the previous lectures. So let us consider simple beam, that this beam is actually we have seen this. So now this is a plane strain beam instead of plane stress beam. Now it is a plane strain beam. Now if I just change my Poisson's ratio, so 0.25 to 0.499, so that means the when the material goes to the incompressible limit, or sometimes it is called nearly incompressible material. That means the any material which is not perfectly incompressible, it is especially the elastic material. Elastic means the area which we are dealing with, it actually all materials are nearly incompressible. So that means Poisson's ratio for nearly incompressible material in linear elastic regime is actually close to 0.5. Now how much close it is? So it depends on how many actually nines are there beyond this point. So 0.499 and 0.499 will have different implication in the solution or the solution technique. Basically I will explain this how it is dependent. Now what here I have shown is that if you consider a plane strain beam with a Poisson's ratio 0.25, you can see that finite element solution and the analytical solution matches quite exactly. But on the other hand, if you just increase the 0.499, that Poisson's ratio is 0.499, if you just increase it, then you will see that the solution is close to this. Now here in both the cases I have used 2×2 integration rule, that is full integration rule. So now the similar thing we have observed when we discussed shear locking problem in case of thin aspect ratios. So or the when the thickness of the beam is very less. So now if I, instead of full integration, if I use selective integration technique, then what will happen, you can see the result drastically improve, even though it is it may not be acceptable, but after mesh refinement and other things we can get the better result. But here we have just kept the mesh constant, so that the mesh effect doesn't come into our solution. Now so if I use selective integration technique, the result is closer to the analytical solution. Now why this is? So to explain that, first we have to understand what is actually locking and why it is arising, what happens to it. Now if you know that in case of plane strain problem, so plane strain constitutive equation, if you remember, I will consider only isotropic case here. So, isotropic case. So, I will explain why I am considering that isotropic case only. Now, in case of isotropic body, what is the constitutive matrix? We all know that is C is E by 1 minus 1 plus mu into 1 minus 2 mu into your 1 minus mu, 1 minus mu and 1 minus 2 mu by 2. So, if you look carefully this constitutive equation, then as Poisson's ratio goes to 0.5, as Poisson's ratio, that is mu, goes to 0.5, then what will happen? This quantity becomes 0, because 1 minus 2 nu goes to 0, and then finally E by 1 minus 1 by 1 minus 2 nu goes to infinity. That means this is very large number. So, now this constitutive equation I can also write it into different form that probably you have that is one is like this. So, so this is plane strain case. So, that is your lambda in terms of Lamé constants, lambda plus 2 mu and lambda plus 2 mu and mu. So, this is your in terms of Lamé constants. So, lambda is the first Lamé constant and mu is the essentially the shear modulus, which is second Lamé constant. So, lambda is essentially, we can write that if you compare these two, then you can find out that lambda is E mu into 1 plus mu into 1 minus mu. So, and mu is actually E by 1 plus 2 into 1 plus mu. So, what happens if the Poisson's ratio goes to 0.5, then this lambda by mu ratio, that goes to infinite. So, as mu tends to 0.5. So, that means this lambda by mu ratio, it is actually determining the rank or the means the condition of this C matrix. So, basically if you another way, if you write this constitutive equation is this, that is in terms of bulk modulus. So, we know what is a bulk modulus. So, bulk modulus is K. If I denote bulk modulus in terms of K, that is bulk modulus. So, bulk modulus, that is E by 3 into 1 minus 2 nu. So, now this bulk modulus also goes to infinity. So, why we are doing in terms of bulk modulus? Because bulk modulus, we know it is responsible for volumetric strain. So, any strain matrix or any strain can be decomposed into two parts. One is volumetric part and another is deviatory part. That probably you have learned in solid mechanics or theory of elasticity course. Now, in terms of bulk modulus, I can write this as K plus 4/3 mu, K minus 2/3 mu, and this is K minus 2/3 mu and K plus 4/3 mu. Now, this is mu. So, now if I say that this bulk modulus will also go to infinity. So, what is the physical meaning of that? That if Poisson's ratio goes to 0.5, then bulk modulus going to infinity means that there is no considerable volumetric deformation in the body. For instance, rubber or any other kind of polymers or soft tissues, those behaves like incompressible material. Now, to solve this kind of problem, which is purely a mechanics problem, with the finite element method, we encounter some problem. So, what is that problem? Let us define. So, if I write my C matrix from this, then purely this C matrix, if I write it properly, then I can write it in this way. That is, if I consider K, this decomposition, that is your 1 1 0 1 1 0 0 0 0. So, this is my bulk modulus contribution, and this is associated with the volumetric strain. So, now another this thing is mu, that is your 4/3 minus 2/3 minus 2/3, then 4/3, then 0 0 0 0 1. So, this is so I can write this is as K into C K plus mu into C mu. So, these C K and C mu are constant matrices. So, this is possible for isotropic case. Now, for an anisotropic case, for instance orthotropic or rotated orthotropic case, this modification is not possible, and for that we will discuss in the next lecture. So, so this is my decomposition of the material stiffness matrix or the constitutive matrix. Now, the similar decomposition, if I write for C, that is in the previous case, that is C is my so I can take lambda common. So, let me write the full matrix, and then so that means lambda plus 2 mu lambda plus 2 mu 0 0 0 0 mu. So, this I can decompose like this lambda as 1 0 0 sorry 1 1 0 1 1 0, then 1 1 0, and then this is 0 0 0. So, here again I can write as I can take mu common, that is this. So, 1 0 0 sorry 2 0 0, then 0 0 2 0, and then 0 0 1. So, this is again I can write as lambda into C lambda plus mu into C mu. So, here C mu and this C mu is different. So, it is a lambda mu description. Now, if I now construct my stiffness matrix, for instance, that what will happen? So, my stiffness matrix, the elemental stiffness matrix Ke, that is actually that integral B transpose C B. So, this if I now substitute in this, so this is in omega E, so elemental stiffness matrix, so integral omega E, so I can write this B transpose lambda into C lambda into B d omega E plus integral B transpose mu C mu B d omega E. So, if I consider my lambda and mu constant over element, so for a particular element if I take it constant, then I can take it out. So, I can just take it out integral. So, now this is my B transpose C lambda B d omega E plus mu B transpose C mu and B d omega E. So, this will give me two components of the stiffness matrix. One is K lambda, let us call K lambda, and another is mu K mu. let us call. So now you see these two stiffness matrix k lambda and k mu are independent of material constants. So if I go for the equilibrium, that means our elemental equilibrium equation, so that is Ke into your displacement vector u and then force vector Fe. So let us call a UE. So naturally my Ke, if I substitute this, so here let us call this Ke. So then I can write it as lambda K lambda E Ke lambda plus mu Ke mu into UE is Fe. So now let us see what happens if I try to solve for this. So for a single element, so this can be, if I take the lambda and mu constant over the domain, so I can also split it like this. So this splitting is possible for global stiffness matrix. So if I try to now for the global stiffness matrix, if I do that, then I will simply I will remove K means E term I will remove. So basically our global equilibrium is F global equilibrium is K lambda into lambda. So this is my global K lambda plus mu into K mu. So this is my global equilibrium into my displacement vector, nodal displacement, which is unknown, and this is my Fe, not Fe, that is my global force vector. So let us call this F. So now if I invert this matrix, so if I write this as U is naturally my lambda K lambda plus mu K mu inverse F, right? So now if you look what happens, if I take lambda common from, or yes, lambda common if I take, then what will happen? So if I take lambda common, that means K lambda plus mu by lambda K mu to the power inverse F. So now if I take lambda outside, it will be 1 by lambda. Lambda is a scalar. So now this is K lambda plus mu by lambda into K mu inverse F. So now see, when as we know that when Poisson's ratio tends to 0.5, that means lambda by mu ratio tends to infinity. Why? Because if I do the lambda by mu ratio, if I check lambda by mu ratio, lambda is actually your E nu by 1 plus nu into 1 minus 2 nu, and mu is your 2 into 1 plus nu by E. So naturally this will cancel, right? This will cancel, and this will also cancel. So 2 nu by 1 minus 2 nu. So essentially this ratio will go to infinity as nu tends to 0, nu tends to 0.5. So that means lambda by mu ratio will go to infinity. So naturally 1 by lambda by mu, that is this quantity mu by lambda, this quantity will go to 0. So naturally if this quantity goes to 0, then this can be approximated as 1 by lambda k lambda to the power inverse into f. So, what is this? What is the meaning of this? That means that the shear contribution, that is in case of a Poisson's ratio which is goes to 0.5, volumetric deformation is supposed to be 0, but shear deviatoric part or the deviatory deformation will be the main deformation. So, but here what will happen, since this quantity goes to 0, lambda is a finite quantity, but lambda by mu ratio goes to 0. So, mu by lambda ratio goes to 0 in the incompressible limit, not exactly 0.5, but let us say nu is for example 0.5 into 10 to the 0.5 minus 10 to the power minus 6. So, you will have 0.4 and then 5.9 will have after the 0.4. So, what will happen? This k lambda is a finite quantity, and this will be naturally this will be large quantity. So, this will make this displacement will be 0, because there is an 1 by lambda term is there. Lambda is also going to, since lambda is having 1 minus 2 nu, lambda will be going to infinity, then 1 by lambda goes to infinity. So, naturally this will give me a 0 displacement. So, which is not the correct thing, because that means the volumetric deformation will be 0, but the deviatoric component of the deformation will be there and will be present. So, that is the main problem we encounter in volumetric in the standard finite element method. So, the way we solve for shear deformation case, that is shear locking, not shear deformation, that shear locking case, here also we use that same thing. That means, if I can suppress the deformation due to this lambda term or this k lambda term, then what will happen is that that mode, that volumetric part of this deformation will not contribute, the unphysical volumetric part of the deformation will not contribute to the stiffness matrix. And naturally, in this expression, that is lambda k mu k lambda plus mu k mu is this quantity. This is my stiffness matrix. So, this contribution, that means if I can suppress this contribution, that means this contribution, then what will happen, that my deformation will be based on this. So, in other word, that or in other way of explaining or thinking this, when lambda by mu ratio is not is very large essentially. So, basically how we treat nearly incompressible material, or how we define nearly incompressible material, is lambda by ratio is very large. So, that means at this component of this stiffness matrix acts as a penalizer to the stiffness matrix. So, this component of the stiffness matrix will try to act as a penalizer. That means, and since the volumetric deformation will be 0, so all the deformation will comes to 0, which is not correct. So, that's a kind of penalty. Lambda acts as a penalty type of penalty kind of parameter in the stiffness matrix. So, all deformation will try to follow the volumetric deformations. So, that's the main explanation for this volumetric locking. Now, to alleviate that, one of the simple technique, which is selective reduced integration. Now, we can do reduced integration, but reduced integration will have a different problem, because we have understood from our previous knowledge that reduced integration will create a rank deficiency in the stiffness matrix, because we are under integrating this strain energy of the material. So, that will create the rank deficiency in the stiffness matrix. While in the selective reduced integration, we are particularly suppressing the particular type of deformation we are suppressing. For instance, here the volumetric deformation, which we know that it will be 0 in case of Poisson's ratio close to 0.5, we can suppress that deformation and we can bring out the deviatoric part of the deformation. So, what we generally do, we integrate this with a reduced order quadrature, and the mu part, that is the deviatoric part of the deformation, the deviatoric part of the stiffness matrix, which is responsible for the deviatoric deformation, we integrate fully, so that we do not account for stiffness singularity of the stiffness matrix. So, naturally, if a in a Q4 element, we have full integration is 4 2 cross 2 point, that is, we know that plus minus 1 by root 3 and weight function is 1. So, now in case of mu, we integrate with 2 cross 2 rule, and here we integrate with 1 cross 1 rule. So, that is your 1 order less. So, this at this point we integrate is 1 cross 1 rule. So, this will suppress the volumetric deformation, unphysical volumetric deformation that will pop up in the in case of full integration. So, this is true for 3D element also. So, even though 3D element we have not discussed here, but 3D element, simple thing that 3D hexahedral element, same thing can be applied, because in the 3D constitutive equation I can write this as simply lambda plus 2 mu lambda lambda, then 0 0 0, then lambda lambda plus 2 mu lambda 0 0 0, and then 0 lambda 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 plus 2 mu, and then 0 0 0. So, this is for isotropic material. So, now for 3D element, if I use my this is mu. So, this is my 6 cross 6 matrix. So, again I can decompose this matrix as lambda C lambda plus mu C mu. So, this is this can be done for the bulk modulus also. So, C mu. So, this can also be used for 4-noded this 8-noded hexahedral element. For instance, if I use the 8-noded hexahedral element, then so here the same thing, that is 2 cross 2 cross 2 rule. So, that means my stiffness matrix for hexahedral element, that K I can write as lambda K lambda plus mu K mu. So, that is here I can use 1 cross 1 cross 1 rule, that means 1 point, that is midpoint of this element. So, here that is the midpoint of this element, and K mu I can use 2 cross 2 cross 2 8, that means 2 point rule, that is 8 point I can use. So, now this is for 3D element. So, this can also be done for the bulk modulus. I can write in terms of bulk modulus, which I have discussed previously here, that is K and mu. So, I can write Ck and mu C mu, so 2/3 mu, so which is more physical, because bulk modulus actually represents the volumetric deformation. So, basically we can now write K as my bulk modulus into Kb plus mu into K mu. So, now here again this I can integrate with 1 cross 1 rule for 2D, and this I can integrate 2 cross 2 rule. This because this bulk modulus B as the bulk modulus we know, which is E by 3 into 1 minus 2 nu. So as mu tends to 0.5, that means this bulk modulus tends to infinite. So naturally this will very large number, bulk modulus will be very high. So if mu close to 0.5, so if bulk modulus is very high, then this will act as a penalty parameter or penalizing the stiffness matrix, so that the volumetric deformation goes to 0. So to avoid that, we can actually use the 1 cross 1 rule to suppress that mode, and then the shear or the deviatoric part we can integrate fully with 2 cross 2 rule and get the solution. So in case of volumetric deformation, when it is 0 in a body, we experience with the full integration rule, we experience in the finite element solution, we experience a volumetric locking. Likewise, in case of a thin structure, like we have seen thin beam, we experience a shear locking. So in case of Poisson's ratio goes to 0.5, then we experience volumetric locking, and this is for linear material. But for nonlinear material, there is no such Poisson's ratio, or even the Poisson's ratio is dependent on the deformation. So there we define deformation gradient. So that means that if F is the deformation gradient for nonlinear material, then incompressible material means that J, that is date of F, that is deformation gradient, is near about 1. So then that way we define the incompressibility in nonlinear material. This is for nonlinear material. So there also we can use selective radius integration to suppress that mode. Now another problem with this selective reduced integration in case of volumetric locking, you can see that this is very well defined for isotropic material, because bulk modulus and shear modulus, they are very much well defined in the isotropic elasticity. But when I consider my C matrix as an orthotropic matrix, that is C11, C12, 0, C12, C22, 0, 0, 0, C66 for 2D plane stress case. Now, plane strain case. Now, here there is no such particular definition of the bulk modulus and shear modulus, because that is direction dependent material property. So here to apply this selective reduced integration will not beneficial, because we cannot separate it out, we cannot make it lambda constant, lambda take out from the this thing, because you have E1 and E2 in 2 direction. That means E1 you have material parameter which is E1, E2, then mu12 and G12. So for this kind of material we cannot use simply like this. Okay, so in that case we have to use a different technique which is known as B-bar method or strain projection method, which is actually considering the mean dilatation or mean volumetric deformation or mean dilatational deformation. We consider that to modify our stiffness matrix. The main ingredient of it, instead of modifying C matrix, why not modify the B matrix, that is strain displacement matrix, in such a way that volumetric component and the deviatoric component or deviatoric strain component separate it out. So then volumetric component we can integrate separately, and deviatoric component we can integrate separately. So this is known as the B-bar method, which is proposed by T.J.R. Hughes in I don't remember the exact year, but that is known as one of the strain projection method or generalization of the selective reduced integration scheme, which is valid for anisotropic material as well. So we'll discuss that in the next class. So we'll stop here today. Thank you.